Before I go diving into the tracker systems and some of the considerations that perhaps need to be thought about prior to using them, I'll give you a slight background on Specialized Imaging for those of you who haven't perhaps heard of us before, because even though we are an international company with offices in America, UK, Germany and China, there are some people that perhaps haven't heard of us before. As our name suggests, we are focused on pretty much a niche market of ultra high-speed imaging and their applications. We were a relatively young company, founded in 2003 by a group, or at least a pair of highly experienced engineers from a company called Hadland Photonics, which later became DRS Hadland when I was there for a short spell. And Hadland Photonics itself was really synonymous with ultra high-speed imaging since the 1960s, developing and designing those systems over that period of time. Some of you have been in research institutions for some time, may be familiar with the Imacon 790 cameras, which was a purely analog system up to about 50 million frames per second. And in the 1990s, the guys that started Specialized Imaging later on were instrumental in digitizing that technology and bringing out the Imacon 468 and then latterly the Imacon 200. And they were capable of up to about 200 million frames per second. In the intervening years, Specialized Imaging has broadened its capability. So we've introduced the SIM range of cameras for some years, which is capable up to 1 billion frames per second with up to 32 images. We've broadened our ability to, in the high-speed imaging market, where we've developed our own sensor and camera, which is now the Corana ultra high-speed video, a really true ultra high-speed video camera capable of 7 million frames per second at full resolution. And then finally, the reason we're here today, or part of the reason here, is to look at the Tracker 2 systems. So generally speaking, we've broadened our capability to develop and manufacture new imaging systems and some of the necessary peripheral devices, not just the tracker systems, but also the triggering and illumination systems. Now, the two trackers that we have developed so far really use the common core technology, and that's a motor which is moving a mirror in order to track the predicted flight path of any particular projectile. So we're not actually actively feeding back into the system, we're simply following the predicted flight path. The core technology of these two is the same, but rather than me trying to describe it, I've got a small animation which hopefully should play without sticking too much, and hopefully the music won't be too loud. It's only about a minute or so, but I'll let this play now. Okay, so I hope that sort of described at least what the Tracker 2 capabilities are. As I say, the core technology of the two systems is pretty much the same. The bigger difference with the Tracker 2 is it's fully motorized in azimuth, elevation and roll of the camera and mirror container, whereas the Tracker Lite is a purely manual system and strictly speaking only designed for horizontal firings only. The scan ratio is a little bit different for both of them, but I'll go through that in a later slide. The positional and scanning accuracy of the two is the same. And although I said earlier we don't actually actively feedback information to these systems, there are some point feedbacks that we can put in at various points along the flight path. Perhaps the bigger difference of these two systems is that the Tracker 2 can pretty much hold any high-speed video camera with up to 800mm focal length lenses, which, if you're looking at particularly big projectiles, is what you really need. Whereas a Tracker Lite is designed around the Phantom and Photon mini type cameras with up to 200mm or maybe 400mm focal length lenses. So getting down to the sort of the nitty gritty of how do we use this tracker system, because it's not a simple case yet of just sticking it in a field, pointing it in the right direction and off you go. you do have to survey in the relative locations of the tracker and the gun or the launcher system. What I've got here is a typical plan view of a horizontal firing where the mirror is arcing through 90 degrees plus or minus either side, 45 degrees either side of a midpoint. We can actually go slightly more than 45 degrees, but for the sake of easy calculations, I'll stick to 45 degrees. So whatever your standoff distance X is, your scan distance is going to be double that. Your start point is typically 1 to 5 meters in front of the launcher or the gun muzzle. This is to allow the tracker to accelerate the mirror up to the speed that is necessary. And also, if you're looking at small arms, then that distance is usually 1 meter. If you're looking at 155 artillery pieces, because of the big muzzle flash, that's typically between 5 and 10 meters in front of the gun. The tracker system and the camera is controlled 100 meters from the tracker system, usually using 100 meters Ethernet cable, so the safe distance behind the gun or the launcher system. Now, I mentioned earlier about the scan ratio, and this is a simple calculation of the maximum projectile velocity divided by the standoff distance X. And if you recall on the previous slide, I think for the Tracker 2 it was 100. So theoretically, if you had a standoff distance of 50 meters, then the maximum projectile velocity would be around 5 kilometers per second. In theory, that's not always the case because you have to allow some acceleration of the mirror. So typically it's about 80 to 80% of this. Once you've surveyed in the tracker and the gun, you have to also input to the tracker system an assumed velocity, because we can't measure the velocity necessarily right at the muzzle itself. So it gives the mirror time to accelerate up to speed. Now, on some ranges, you might not have that kind of standoff distance available if there's trees, wire fences, buildings, and other obstructions in the way. So we can skew the position of the tracker system to either be a little bit more towards the gun muzzle or to a little bit towards the target. So you can still maintain that scan distance, but you have a slight perspective difference, which may be useful. If you're looking at missiles, and if it's a wire-guided missile, for example, then you may want to look at the wire guiding, the wire coming out of the back of the missile. Or if you want to look at the tip of the projectile to see what the heating is, as Stefan is going to describe later, then perhaps you want a slightly more frontal perspective. So really, in order to prepare the ground for the use of such a systems, you do need to survey in where the tracker and the launcher is relative to each other. Obviously, you need to know the direction of the intended projectile flight, so you can accurately measure that standoff distance, which is quite an important distance. And typically, we can get down to 5 to 10 centimeters accuracy on that, and also the distance between the trigger and the start point. You need to input the projectile muzzle velocity as well to give the mirror a fighting chance of catching up with it in good time. If you have a drag coefficient related to the projectile, that can be inputted into the tracker system. And also, if you have an accelerating projectile and you know the velocity profile, that can also be added in as well. So it's not just a one-trick pony. We can look at other projectiles as well. Now, going back to the horizontal firing view from before, for a standard horizontal firing with a gun elevation of 0 degrees and a 50-meter standoff, your scan distance is 100 degrees, as we've established. But the azimuth, elevation, and roll of the camera mirror pod is pretty much all 0. An interesting point here, which I'll touch on later, is that even though your closest distance is 50 meters, your furthest distance is just under 71 meters, which can present some difficulties, which I'll touch on again a bit later. Now, what happens if you want to incline the gun? Whether that's just a few degrees because the projectile isn't hitting the target and you need to raise the gun elevation, or you want to do inclined indirect fire of an artillery piece. All these distances you have to measure are now suddenly up in the air, which are much harder to measure. But luckily, what we do in order to set the system up is we assume you do horizontal firing first and measure out the plan and the positioning of the tracker relative to the launcher. And the only additional measurements you have to do for an elevated firing is the gun elevation, the distance between the pivot point of the gun or the launcher to the start point along the ground, and the barrel length from the muzzle to the pivot point. So the plan view will go from this to this with a slight skew. And the standoff distance goes from 50 to 63 meters if you have a 45-degree elevation, and your scan distance then goes from 100 meters to 141 meters. So things do change, but perhaps the most important thing is the azimuth, elevation and roll becomes a really non-trivial solution, because your tracker and gun and start point are all fixed relative to the gun, relative to where the projectile is going to be flying now. And your furthest distance away is now 93 meters. So if you're doing an incline firing, together with all the other survey information that you input into the software, you need to know the trunnion to start position, trunnion to muzzle, and also the gun elevation. Luckily for everybody, the Tracker 2 software, control software, can calculate the correct angles and position itself automatically. So there are other considerations, not just the tracker and the survey and everything else, but what kind of camera are you going to put into this system? Whether it's a thermal camera or a high-speed video camera. Typically, frame rates are between 2,000 and 10,000 frames per second, depending on the speed of the projectile. Because we're following the projectile rather than it passing the field of view, we can have slightly longer exposure times. So typically between 200 microseconds and 50 microseconds. What perhaps needs to be thought about a little bit is if you want to, on the day of the test, speed up the frame rate, that's going to reduce your field of view. And here's an interesting point where if you have a focal length of lens, because your distance from the tracker to the projectile is varying throughout the flight, so from the two ends of the track it's going to be further away than at the midpoint, then that field of view is going to be changing. So again, you perhaps have to consider your camera pixel resolution and the camera pixel size if you need to think about what kind of frame rates you need in order to get enough temporal resolution. And the final point here is really an often overlooked aspect of using a tracker system, and that's partly down to this changing distance from the projectile to the tracker, where because of the changing distance, you have to change the f-stop to increase the depth of focus, and typically you're going to have to reduce that down to a number where you increase the depth of focus enough to keep the whole track in focus. That then brings into play perhaps the camera sensitivity, what pixel size camera you use, and also the ambient lighting conditions. I'll give you some examples here of a field of view change. If you had a sensor that was 1024 pixels wide with a 50-meter standoff and it's 10 micron pixels, these are the kinds of fields of view that you would have at the beginning and the midpoint and the end point for these focal length of lenses. So if you're looking at a long rod projectile, it's about a meter and a half long, you might be looking at a 200 to 300 millimeter focal length lens. If you're in order to get a more sensitive camera, then you have a 20 micron pixel, then these fields of view are going to double. So you would potentially have to double your focal length of lens as well. What we tend to use as a matter of, at least for demonstration purposes, to make our lives a bit easier, we use zoom lenses. So from 120 mm to 300 or 300 to 800 millimeter. And sometimes we use doublers or teleconverters to extend that even further still. And to touch on the depth of focus that you require during a track. If your standoff is again 50 meters, your required depth of field is quite a large 21 or just under 21 meters. So for a 600 millimeter lens, and these values here are really for a theoretical lens, so for a real lens it might be a little bit better. For 2.8 you're only going to get a 1.3 meter depth of focus. For f11, 4 meters, and for f32, 11 meters. Now f32 is really shutting the lens right down, so you need an awful lot of sunlight in order to see anything. It would be quite dark otherwise, but you do happen to have just under 12 meters of depth of field. If you focus the lens at the 30-degree point, and when I say 30 degree, that's 30 degrees in the arc of the mirror, then these are the kind of focus limits that you've got. And how do I know this? Well, the software that you get with the tracker allows you to, or includes a lens calculator, so you can put in camera parameters, lens parameters, and tracker parameters, and from that you know what your field of view is going to be depending on the pixel size and focal length of lens and resolution, and also what your lens focus is going to be in relation to the various distances. So those are the general considerations if you're thinking of using a tracker system where you need to survey things in, you need your predicted muzzle velocity, and some of the considerations for the high-speed camera and the lensing and the f-stop that you'll need for sufficient depth of focus. Now, two other considerations perhaps that need to be thought of. for this particular type of presentation. One is that with IR cameras, you probably are going to have to remove the glass of the tracker system because most of them won't transmit IR frequency light. And also sometimes projectiles don't always do what they're supposed to do, and they can do some rather strange things. Now, hopefully this video, some of you might see this in rather jerky fashion, but when you download it or view it after here, this should be quite nice and smooth. The top projectile is pretty much behaving as advertised, but the bottom one is clearly not. It's breaking up, changing its drag coefficient, and probably has a different muzzle velocity as well. So how did we manage to keep both those projectiles in the field of view throughout the track? What we do is we place detectors under the field of view which can detect the passing of the projectile over the top. So if you want a position change, so perhaps the trigger was a little bit early or a little bit late, you can use a single trigger. If your velocity, predicted velocity, is incorrect or inaccurate, then you'll need 2 trigger systems with a known distance between them. And all this can be surveyed in and put into the tracker itself. And of course, if it really is unpredictable, you can put up to 5 or 6 further down range in order to make sure that the projectile is going to be in the field of view. And this is a typical sky screen type of projector. This is the one we make, but there are other ones out there as well. And by way of example, here's a 3D tracker system that we had, one tracker either side of the flight path, looking at the similar Huygens probe that Stefan is going to be talking about with his thermal cameras. And in early stages, you can see that the projectile itself was almost outside the field of view. And with 2 detectors, we managed to put it right back into the middle of the field of view. So the system does work quite well.